We are live, Cooking with Gas. Hi, everybody. This is Steve Miller, better known as Kelly's dad and the marketing gunslinger. And welcome back to part 3 of the webinar series for the MTConnect Student Challenge. I guess I could take these glasses off. I guess I'm orange enough in my face to, none of us are in our offices, right? Is that correct, right? Because I know, Will, you said you're in La Jolla.
I'm at a IIC meeting here in La Jolla.
Yeah, okay. And Helena, you are, where are you?
I'm in Troy, New York.
In Troy?
That's right.
New York. Okay, I know Troy, Michigan. But
north of RPI.
And I am in Washington, D.C. So we are all over the place, and but not in our offices. So we don't have our usual cameras and everything like that to make us look pretty. And I'm using terrible hotel room lighting and stuff like that. But anyway, be that as it may, thank you again for joining us for part 3 of the MTConnect Student Challenge webinar series, where we have been going through a video workshop seminar that Mr. Will Sowell, who is right there underneath me, put on. Today, however, you get him live. Boy, I'll tell you what, we are jazzed about that. So let me quickly introduce you to the illustrious gang right here. Got Helena Hailu, and Helena is, if you don't know who she is the boss. And hi, nice wave, Helena. She's not looking down on us. I see you changed your camera angle, so that's nice. She's the MTConnect product manager for the MTConnect Institute, part of the Association for Manufacturing Technology, where I was this week. And Tim Shinbara. Wait, that's a misspelling of his name, isn't it? Isn't it Shinbara?
Yes, it is. It's Shinbara.
How come none of us caught that in the other webinar? Well, he's not here, so we won't worry about that. But
we just call him Tim Shinbara.
Yeah, Tim.
I just didn't want to embarrass you.
What? You should have told me. But anyway, and then Mr. Will Battelle Sobel, Will Sobel, who is Chief Strategy Officer for System Insights Incorporated and the godfather of MTConnect. And first of all, before we get started into Will's part of the presentation today, let's just do a little quick recap of what is the MTConnect Student Challenge. And Helena, I want you to share that with us right now.
Steve, the MTConnect Student Challenge is an innovation competition that's sponsored by the Office of Secretary of Defense, Defense-wide Manufacturing Science and Technology Program. It consists of 2 distinct competitions. The first competition is the ideation competition, where we would like students to submit a 5-page proposal of something that would make an impact within the manufacturing industry. And it should use the MTConnect standard as part of the solution. The deadline for that is December 15th. The prizes range from $5,000 for first prize to $1,000 for the third prize, third place winner. There will be 3 third place winners, so that's a total of 5 prizes.
Nice.
Yes. The application competition, which again is completely separate from ideation, is one where we're asking students to create software applications that use the MTConnect standard to, again, impact in a positive way, impact the manufacturing industry. The deadline for that is January 31st, 2016. There will be 3 prizes. Top prize is $10,000, second is $7,500, and the third prize is $5,000.
That's really nice.
That is about the competition.
Yeah, that's great. That's great. And who can participate in this?
The competitions, both competitions, are open to U.S. community college and university students at the undergrad and grad level. Anyone who has been legally admitted to the United States, that includes international students, can participate.
Okay, very good. And we'll go into some of the other aspects of the student challenge when Will finishes with his part, okay. And then of course give you contact information on where you can go to get more information, as well as where you can go to apply for it and get your other questions answered. But we want to, we've had two very in-depth presentations on our first two webinars. Those are being archived, and anybody can watch those can do so. Helena, are those available yet, or are they?
Yes, they are.
Are they up yet?
They are up on YouTube, and we will put a link to them from the mtconnect.org/resources page.
Okay. Okay. Very good. So with that, I'm just going to get right into it, and I'm going to get rid of this little visual right here, and I want to hand off the controls to Will, because Will, I know you've got a lot to talk about and cover. You said you're going to review a little bit of what we saw in the video last week. So Will, why don't you take over and rock and roll, and we'll pay attention we'll actually pay attention to what you're saying. How does that sound?
That sounds excellent. I always like when people pay attention.
I'm going to go ahead and pause my screen so that nobody gets distracted by me over here. So.
And I'll do the same.
Hopefully I know how to operate.
All yours.
So we left off right around machine to machine. I wanted to go over that this time, and if it's a little bit of recap, sorry for repeating myself, but hopefully we can go a little bit slower. So let's see. Is this being, did I just advance the slide correctly?
I'm sorry, what?
Did I just advance the slide correctly? Because I'm not quite sure which window it's on. I have three windows here.
This is the window.
Okay.
Okay. There we go. You got that arrow there in the bottom left corner there?
Yep, I got it.
Okay.
So we looked historically at how machines, this part of the talk is about machine-to-machine integration, a novel way that MTConnect, with its standard, has solved some of the problems of connecting various pieces of manufacturing equipment together. We looked historically how manufacturing equipment, robots and machine tools and other pieces of like conveyors and so forth were connected. It was all through wires. So this is actually a picture of the Haas Ready robot option in 2014. Most other controllers have a very similar type of connection to them, which is basically some terminals and 24-volt wires. The problem with that is that it doesn't really allow you to send anything but binary ones and zeros between machines. And if you look at the way we currently hook up equipment, you have a central cell controller and then multiple PLCs, which then interact with the actual equipment. And each one of those PLCs is then customized, and the central cell controller is also customized for that solution, as well as the software on the robot and the machine tool. What we're trying to get to, and what the MTConnect implementation of device-to-device or machine-to-machine, uses a read-only interface where we're dealing with high-level semantic models of the information. So instead of raising a wire from a 1 to a 0, we talk about the actual task that you'd like the robot to perform. So if you think about information models, we can pass a lot of information. We can tell it about the part that's being produced, what the constraints are on that part, what type of material, and so forth. So the machine and the robot can have an intelligent interchange of information and can coordinate activities, and the robot's intelligence can actually allow it to schedule and optimize material flows. So we think about it also, because we've gone to a higher level of reasoning, we also have safety and security by design. the two devices are just observing each other. We don't have the same level of centralized control where basically the central controller is responsible for telling everything what to do. Here we have devices making decisions about themselves and then communicating that information to the other devices in a way that allows for a much more sort of self-aware system. The machine itself is controlling what it's doing and will not take an action unless it knows it's safe, and will not respond to another request unless it knows it can do that in a secure manner. So this gives us a lot more control over distributed processing and device coordination. So if we look at this, basically we've distributed the intelligence out to the devices, taken it out of the central controller, and moved it out to the edge. This allows us to do things like handle failure in a much more elegant fashion, where if you have a central controller, basically you have a single point of failure. Once that single point of failure, if that central controller dies, basically your whole production is out. By moving the intelligence out to the edge, you can actually have devices self-organize and work around problems and reroute or reschedule on demand based on their own knowledge of what needs to be done to execute these processes. There's a little video that I put together before, I think because I've gone through most of it. Basically, we're using read-only semantics. So basically, each device only reads information from the other one. We don't write back. So they observe each other's state, and by observing each other's state, they then make decisions about what to do. And it's a much easier, much simpler way of putting multiple different devices together. So we've got an initial implementation in MTConnect that supports this method of interaction, and an area that definitely we want to see taken further as we start to get into dynamic orchestration, dynamic routing and scheduling of material. So now I'm going to talk a little bit about some research projects that have been done with MTConnect. These are just to give you some examples of how MTConnect has been used in the past to do some really amazing things. And first one I'm going to talk about is a project that was done over at UC Berkeley at the Laboratory for Manufacturing and Sustainability that was done by Ronak, who's one of the grad students there. And it's a really interesting project. Basically what he was doing is he was trying to figure out how to get data from machines and simulate or predict how much energy was going to be used given various different strategies for making a part or a series of features. So the project collected data from the machine tool, so basically given external sensors and the actual machine tool data, the data was then fused together and put into a data processor, which was then analyzed. And the knowledge abstraction is basically the analytics. When you turn that raw data and you fuse it together, you turn that into knowledge. And then by looking at that knowledge, you can then figure out how to optimize various different process parameters. You also take in past experience. So there's also some first principles and other information that is used to be able to drive the optimal machine models. The work was done on a Morisaki, so basically we had a machine control. We then had an MTConnect adapter sitting on that controller, or next to the controller, that was collecting information. As well, we had a high-speed power meter that was collecting 100 Hertz data and from the 3 phases of power coming out of the machine, or going into the machine. And then that data was then aggregated together in the MTConnect agent. And this data was then collected and correlated and put into a database. That data, after it's condensed, can then be used in a simulation process. The data, so this is a direct data that we were getting from the machine tool. So you get things like feed, speed, power, position. So you have a 3-dimensional position, as well as loads and what is currently running. By using that data, you can then derive other data, such as the duration, energy, and so forth that's being used in a particular cut. And then you can take that indirect data and compare it to your simulation. So this is another way of looking at the entire stack. So we have a number of different sensors coming in. We have the MTConnect agent, which is aggregating all the data together, processing, simulation, compiling, and then generating models. So when the data was taken together, basically we looked at all these different parameters of how, or all these different characteristics of that particular feature as it was being cut, and looked at the energy consumption for each of the blocks of code. And by doing that, we were able to determine what energy was used to be able to do any one of these operations. And we can then, using a test cart and various different features that were made in it, attribute that amount of energy to each one of those different features, and then figure out in a predictive manner, because we have similar features that appear in different types of parts, we can then predict how much energy was going to be used for a particular toolpath in a tooling strategy. So this is basically different strategies for making the exact same, or doing the exact same set of operations, or making the exact same set of features, sorry, and what the most efficient way is of actually making those features. So that's one project. A similar type of project, again, around energy. This was done in IIT in India in Chennai by a number of grad students, overseen by Athlon, my co-founder of System Insights. And the idea here was to be able to simulate how machine tools use energy. So basically being able to take a number of sensors and hook them up to a test rig and then be able to reverse out how a full machine tool will operate by being able to simulate various different components of that machine tool. So basically they hooked up a two-phase AC motor to a DC generator and then had a resistor bank with a number of relays which turn on and off the resistors. And that was all controlled by an Arduino that would turn the resistors on and off. And then they would also control how much power is being put into the three-phase motor to simulate different speeds and different loads on the motor. And one thing they found out was that you had to sample at a fairly high frequency to be able to get the different, to get the shape of the energy being used. So if we look at this graph here, basically if you only sample at a 1 hertz rate, you miss a lot of the detail. All the spikes went away. Even if you sample at, let's say, a 10 hertz rate, you miss a lot of the spikes. If we go to 100 hertz, we start getting a lot of the detail that we need. I think they tried to sample at a faster rate and found it didn't offer a huge amount of improvement. So 100 hertz was pretty much what we settled upon. The next thing is looking at a recurring machine cycle. This is an actual cycle that was captured from a real machine tool. They were able to find certain patterns in the data. And by looking at those patterns, they can then identify various different operations of the machine. In other words, when the machine starts up, then when it's ready for operation, sort of an idle state, and then you can see the pattern when spindles start and spindle accelerations, as well as the point at which the tool actually engages with the material and then starts removing material. You get that load spike, and then you can see it spin down, and so forth. And this slide, what they mean by operational and unproductive power is the power difference between sort of a theoretical and the actual. By looking at those different patterns now, we can then take the real machine tool energy utilization and map those patterns back in and look at how the energy was consumed over this period of time and how these different, how the simulated patterns then map to the actual pattern. By looking at things like load levels and different spikes to simulate rapids, so when that machine tool is moving in a rapid manner versus the motor starts, you can start to see these patterns emerge in the actual data. And then, after they were able to do this, they were actually able to find that they could very closely match a real tool with their simulator. So they had all these patterns, they knew how the machine behaved, and they had a simulation of how the machine should behave, And then they were able to take data and match it up, and basically got within a really close coefficient, basically at 0.82, almost 82% match of the actual machine tool behavior just by collecting data and then analyzing it and then being able to build models. Another one that we did again in IIT in India was a 3D printing project where the objective was to be able to find what process parameters are most closely related to the accuracy and the quality and strength of a part. So they picked a number of different control variables, 7 variables for dimensional accuracy and 7 variables for strength, and then used just an off-the-shelf printer and open source slicer software, and then held some things constant so that they weren't varying everything. So ambient temperature and fit values and various other control variables were held constant, and then they varied the 7 different parameters to see which were most highly correlated with a couple of different, with these 2 different factors. So they made a little box, and they tested the box for strength and quality. Using the quality was done using a vernier caliper, and they used a ultimate tensile strength UTS test stand to test 2 things, both the elastic modulus, basically how stretchy it is, and then how strong it is. So stress, strain, and flexibility. What they found is that some things are very important to strength. Basically, extruder temperature was important to the elasticity, but not so much for the strength. Infill pattern was important to both. Slice height was very important to the strength, but didn't really matter too much when you're talking about the elasticity and the modulus. And the infill density had an important role in the strength as well. And by taking these, they were then able to figure out also what had importance for the accuracy. So basically how accurately the print was made, and they found that actually the X and Y axis intercepts were some of the most important factors in that. So you can use MTConnect to be able to collect data. This is an additive process for various different processes. You're able to use it to do some really very interesting research without a huge amount of cost or kit. So I'm going to switch gears a little bit. I'm going to start going through some of the information models and what is actually in MTConnect. MTConnect consists of 4 high-level information models. You think about it this way. There's a devices model, a streams model, an assets model, and an error model. I'll go over each one of these in a lot of detail. But before we get into that, I'd like to go through a little bit about XML. So if you don't know much about XML, been around for a long time. If you've ever used a web browser, HTML or XHTML is actually built upon the XML standard. And it is a way to be able to represent data in a very simple, human-readable manner, so it's very easy to interpret. And it's also the X is for extensible, so basically you can extend it to include additional types and data very easily. And we have some examples of how to do that in MTConnect as well. And there are 2 different ideas in MTConnect, in XML, where you have either well-formed or valid. Well-formed means you're basically adhering to the basic structure, and valid means that you are valid within an XML schema. So we have an XML schema associated with MTConnect, which you can then validate against. And the other thing that we use is XTAC, which allows you to select various different components of the XML document. So this is an example of an XML document. We have elements, and then elements can be arbitrarily nested into sub-elements. Elements can also have what are called attributes, and attributes are a way to be able to assign certain properties to elements. Elements can contain either what's called C data, which is basically just text the text of a paragraph within an element, or else a number of additional elements. And if you look here, you have things like an author that has a last name and a first name, and the name is actually embedded inside the data. The address has a street, a city, and a country. Postal code will tell you what country is associated with that postal code as a property, and then the postal code itself is a key data within that. Every element must have a close element. So you have which is leading with a /, so same mirrored element name on the other side with the / in front of it. As well, to close out an element, a simple element, it just says attributes, you can just skip the close element and just put a / and a right angle bracket, and that does everything. So within XML, because it's a pretty open standard, you can pretty much name your elements however you want. You can name your attributes however you want. We provide a style guide, and all elements are given in what's called camel case. So the first letter of each word is capitalized, and the words are then put together. Attributes are in what's called snake case, which basically the first letter is lowercase, and then each word is after that is uppercase, and the words are stuck together. When there's a value for what we call control vocabularies or for various different semantic values like ready, active, so forth, words that we have standardized, they're all in uppercase, and we use underscores to separate the words. These are going to be in the value of various different elements, and you'll see that as we go through the standard. So it gives you sort of just an idea of whenever you see words in a certain format, we're consistent throughout the entire standard. We then have these grouping elements also, so things that are usually pluralized, like devices, components, and data items, and so forth, are used as containers of other sub-elements. The use of XPath is so that we can then find various different elements within the document. So XPath is also a W3C standard, and we're just using it and referencing it. So when we want to, let's say, find in this document the author, you can find it anywhere in the document by just putting a / author, and that's going to give you all the elements that are that have an element named author. You can also then put some what are called predicates or conditions on that request as well, where you can say, like, if one of the attributes, you can only select an attribute, so at living basically says that the attribute living is equal to no, and the attribute famous is yes, then select that attribute. So you can, it's almost like a query where you can specify exactly what elements of the document that you want to get back. And you can specify full paths, or you can specify a relative path, any element underneath the root element where this exists. So now to go through the different types of data you can get back. So the first type of data, which we have in MTConnect, is called a probe. The probe gives you all the structure of the device that you're going to be getting data from. And probe is giving you semi-static data. So you don't do a probe all the time because the data is not going to be changing all that often. It's pretty much the configuration, the structure of the machine, the components, and the type of components, and then the data items within those components, as well as other things like the configuration and various other what we call metadata, which describes the structure and the types of data that you're going to get back. It also tells you things like the units and the representation of the data and so forth. So we look at an example of what this looks like logically. You have a set of devices, and then each device is made up, can have data items, because the device is actually a component, meaning that it has the same structure as all the other components. And it can have data items. And here we have two examples of availability and emergency stop as two data items. You then have things like axes. An axes is, again, it's kind of a container component. It then has a linear X, Y, and Z, and a rotary C. This is a simple like 3-axis machine type construction here. Each of those axes has a position and a load, and the rotary C axis, the spindle, has an angle a rotary velocity, and a load. Then we have things like a controller abstraction that has these are just conditions, and then a path underneath that. Each of the paths, so controllers, if you have a complex machine, can have multiple paths, multiple tasks that can be doing at the same time. And each of those tasks in MTConnect are broken out separately. Here's what it actually looks like in XML. So we look at the top level. We have the MTConnect devices. Every document in in XML must have a single root element. In the devices document, that's the MTConnect devices. A lot of the attributes that you see there of that top level element, like the XSI, those are namespace declarations, and those are part of the XML standard, which tells you how to validate, how to understand what this document means, or how to make sure the document is correct. And the schema location tells you where to find that. So this is telling us that the location for that name is actually right here locally in the MTConnect devices XSD, which is a schema document. We then have what's called a protocol header that comes next. That's what the header element is. And that has things like the time the document was created, the buffer size and the sender of the document, and then a little bit of information about things like how big the buffer is and what instance of the agent is running, so that allows you to tell when things like the agent is restarted. Get into that a little bit if we get into the protocol section today. The device has a description which tells you a little bit about the device, who the manufacturer is, the model of this device. Every device itself must have a name and a UUID. The UUID is a universally unique identifier that's associated with the device and allows you to identify this device as opposed to all other devices that are currently in this environment. And you also have to give it what's called an XML ID, and that just allows us to be able to uniquely identify this particular XML element within this document. And every component has to have an ID. Within that, we then have what are called data items. And the data items, if you look at the way the data items are constructed there, we're going to go into a little bit more detail in a second. Basically, each component can have a list of data items. And that's a type of data, the pieces of data that this component can give. And then if we go down a little bit further, we have a set of subcomponents. So devices has components, and axes is another component. And axes actually has more subcomponents. I can press it down and remove the components element between axes and rotary, but there's additional elements. There's additional components that are then below axes, like rotary and linear and so forth, which are then part of that hierarchical structure and gives you the context then. So if I have the spindle speed or position or rotary velocity of a particular data item, I know which component that's related to. So this is a top-level element. So we have here, just goes through some of the information I told you about before, the namespaces and the location and so forth. The data item itself has various attributes. So basically, a data item tells you what data you can get back from a component. And in this case, top-level data item, let's say availability. Now, availability is actually the only data item you're required to provide in MTConnect. So it's called an event. An event is something that represents either the state or something that occurred on the machine. And we have 3 different types of data items, and I'll go through those in a second as well. The type and the ID and category are the only things that are required in a data item declaration. And when you have a sample type, you're also required to tell us what type of unit are used for that sample. So that's why it says, that's why there's an additional note. Each data item, for each type of data item has, for a sample, has a fixed set of units that are associated with it. So like the rotary velocity, has a number of revolutions per second, or sorry, per minute. Position is in millimeters and so forth. We also have a lot of other attributes which are optional. Things like you can say what kind of native units were used in this data item. You can tell us what the coordinate system was, either work or machine. Statistics like average and so forth are also represented. Number of significant digits, the sample rate that this is going to be sampled at, and so forth are all given. We can also have what's called a couple of elements that occur below it, which are things like a source. You can tell us what was the source of this data. If there's another data item that's actually in a different component even, that's providing the data for this data item, you can represent that as well. You can also give us the minimum and maximum values and any kind of filter constraints that are put onto this data item. So 3 different types of data item are, again, event, sample, and condition. Events represent the state, and we have this new thing called discrete, which in discrete you can have messages or counts that are associated with a data item. For state-based events, you'll only get a single value and then only updates when it changes. Every single, like if you, let's say you're collecting data from a device every second, you won't want to say that you're still in the same state every single second. So what it does is basically does what's called delta compression. You only send data when things change. This isn't true for things like discrete events. So like, let's say you have a message that's coming out that says the door is open. And every time the door is open, you want to send that message. Well, then we have what's called representation discrete, which tells us that that message can repeat. And we don't have, and that every event that occurs of that type is significant. So every time the door gets open, a message gets sent that the door open. The door is open 3 times in a row. You want to have all 3 of those events actually appear. If you were compressing deltas, you'd never see the second and third instance of that event. Samples are continuous variables, second type. A sample represents data that's collected continuously, but we're only sampling at a certain frequency. So there's going to be data that, or values that occur in between the sampled points. The idea is that you can interpolate in between samples. Samples are always floating point values, whereas events can be any text or controlled vocabulary. A sample is a floating point value that always is represented in some kind of units, and they must have some form of units. For an MTConnect, we've actually standardized all the units. That makes it a lot easier when you're doing data analysis. You don't have to try to guess what the units are that the values are going to be coming out in. A position will always be in millimeters. A path feed rate will always be in millimeters per second. If you have a displacement, it's going to be in decibels. So MTConnect makes it a lot easier for the application. You don't have to worry about, is this temperature in Fahrenheit or Celsius or Kelvin? It's always going to be in Celsius. So you don't have to worry about units conversion or checking some other data item to check what the current units are that are being used by the machine at this point in time. The third type of data we have in MTConnect is called a condition. A condition represents what are typically called things like alarms. And when we call them conditions because it represents the condition of that particular component for a particular type of data. So let's take the temperature, for example. The temperature is going to tell you the condition of this component with respect to the temperature. And if, let's say, the temperature is normal, in a normal range, the condition will give you a normal. When the condition is when the temperature gets into not a critical state, but at a level that you're worried about it, somebody should pay attention. If it gets any hotter, it's probably going to fail. That's a warning. And then a fault is when intervention is required, human intervention, or the machine has to be shut down to be repaired. So a fault indicates that the machine is actually in a state where we now have to take action. we decided that we were going to only have these 3 levels for conditions. We'll talk more about that when we get to the streams document. The source of the condition can also be specified. And this is, in the example here, we have a sample, which is actually the real temperature, and then we have the condition, which is based upon that temperature, and the two can be linked together using that source reference. The next document is the streams document. So now we know what type of data, we know the structure of the machine logically, we know what components it has, how many axes it has, and with respect to those axes, what type of data we can collect from each one of those axes, whether it's, let's say, in the case of an axis, it's position, let's say, load, and rotary velocity, and angle, and so forth. In the case of a controller, we want to know what the state of the controller is, whether it's in a executing code or automatic manual data input, these kinds of things. And MTConnect represents all of those. So, but that just tells you what type of data you can get. It doesn't tell you what the actual values. The devices document does not give you any of the values of the data. It just tells you what type of data and the relationship of that data to the components. Streams tells you the actual values of the data. What we've done is we've flattened out the hierarchy. So you don't have that sort of nested hierarchy anymore. You just have a flat set of data where you can see the complete history also. So when you flatten it out, you can also give multiple values at different timestamps for each piece of data, or each value for each of the different data items associated with that component. And we've tried to balance out between enough information within the streams to be able to refer back to the devices and the amount of overhead it takes to be able to represent that data in X amount. So we look at a streams document. Basically, each of the component is broken down into what's called component stream. That's going to reference the component that we had back in the devices document. And then you'll have, for each one of those, either samples, events, and conditions, or maybe sometimes it's samples. There's only samples, data items, sample category, or conditions, or vice versa. If we look at the document, so this is going to be a little bit of preview of what we're going to talk about in the protocol section. We get the protocol. Basically, we have these 3 separate requests: probe, sample, and current. The current provides sort of a snapshot of the current state of all of the data items in all of the components. So you can basically figure out, okay, this is where I am right now. And then sample, you can then get a delta from that point moving forward. In MTConnect, what you usually do is you'll first do a current to get the current values of everything, and then you'll do a sample, which will then give you all the deltas from that current going forward. And using this methodology, you can then never miss a piece of data or any data coming out of MTConnect. And we use timestamps, and everything is timestamped in MTConnect in the samples document. And that allows you to assert both contextualize the data in time, which allows you to assert causality. The document looks like this. So basically at the top level, we have, again, the MTConnect streams root element, and then the header information, which tells you a couple of different things. The next sequence number we're going to pick up next, the first sequence number in the buffer, and the last sequence number in the buffer. And that's going to be covered more when we get to the protocol section. In the device stream, at the top level, for each device, we have what's called a device stream. That references one of the devices back in the devices model. And then for each of the components in the device stream, we have what's called a component stream. And that has a sub-element called samples, again, a container. And then you'll see various different elements like here we have spindle speed that's been renamed rotary velocity in the current version. And that will give you the rotary velocity in revolutions per second, or sorry, per minute, with a timestamp. And it gives you the type and the subtype as well. Type is then turned into this, into the element name itself. And you can also see things like in the controller component stream right there. You see path down below. And in the path, we have the block that's being executed. We have the controller mode, we have the line, the program, which is basically the program name, and the execution state. And all these are represented in the same way. Basically, the element name is the component, is the data item type, and we represent the subtype and the sequence number, which is used in the protocol, and then the timestamp that thing occurred. Timestamps are very important because without timestamps, you really can't analyze data. You need to know when things happen in time. So going a little bit more into the header, we have again the common elements or attributes: the creation time of the document, the sender of the document, the instance ID, which allows us to understand if the agent is restarted. We can detect that by looking at the instance ID for each restart of the agent will change, which allows us to know whether we can carry on from where we left off. So I'll talk more about fault tolerance when we get to the protocol section. But with MTConnect, you can always pick up where you left off if you get disconnected from the agent for any reason. And you basically use their sequence numbers, the first, last, and that sequence number to be able to find out where you are in the buffer and to be able to carry on from where you last got data. In the streams document, we have these device streams, and within each of these device streams, we have the component stream. And each component is flattened out. So this is a single component, and we provide the name of the component type, which is right here, the rotary, and then the component identifier, and that refers back to the ID within the device's model. And in the component stream, we have these three different groups: events, samples, and conditions. And for samples and events, we can only have one value at any given timestamp. Something can't be in two places at the same time. So let's say a position for a sample, you can't have that axis in two positions at the exact same timestamp, so we only allow one value at any given timestamp. If there are two values, that's probably a problem with the way the data was reported into the MTConnect agent. The sequence numbers are not the same as the timestamps. Sequence number are the arrival order of the data into the agent. So you could actually, because of various latencies within the network, you'd actually have two pieces of data, and the timestamps may be opposite of the sequence numbers. So they arrived in a different order with respect to how they actually occurred in real life. That's why we have the two things. That's why you should always use the timestamps when you're trying to figure out when data was actually reported, not the sequence number. Sequence number allows you to never miss any data. Now we talked about the types in the data item in the devices model. The way it's converted into the element name in the streams document is basically since remember the rules back before, any controlled vocabulary or value of an attribute needs to be all caps with underscores. Basically what we do is we capitalize, we take the two words and we put them into camel case. So we capitalize the first letter, the rest is lowercase. We combine the words together, so controller mode will be turned into the element controller mode, where the first letter is capitalized. Same thing for execution. Single words are pretty easy. Then we talk about, just to sort of refresh, we cannot have two adjacent values at different timestamps with the same value, so they must be compressed down. So in the first example, we have two values occurring in sequence, both value automatic. That's incorrect. We can only have them change. So automatic, manual data input are correct. We only represent data that has changed, so the deltas. Discrete, again, to refresh that one as well, is the exception to the case. The two cases I have here, which are pretty much the only two cases we have in MTConnect right now, are things like part count. So I want to be able to say if I have a discrete part count, the device that's producing data for MTConnect only knows about when a part is produced. Maybe this is just like a light sensor. And all it knows is that when it gets tripped, another part has been produced. Therefore, we'll give 111. Basically, that means that one part is produced. Because we know it's a part count discrete, we know that this is not a delta, in other words, not going 1, 2, 3, but this is actually the number of parts that are produced at that point in time. And the same example I gave before with door open, we want to make sure that every time that event occurs, we get that message, and none of the messages are compressed. Samples, again, will always have units, and so we know that, like for a path feed rate, it's always going to be in millimeters per second. And we don't repeat the units because the units are given in the devices model, and there's no reason to repeat that every single time for every single value that we're getting. And again, these are only changes. So if your path feed rate is 0 and doesn't change, it will only be reported once, and only when it changes will then be reported again. MTConnect also supports time series data. And this is a way to be able to, it's a little bit more efficient than trying to repeat the, like in this case, it's audio data. So this is waveform. And if we had to repeat the individual samples every single time, it would become very, very costly as far as overhead is concerned. In this way, we can basically put them all into one chunk and report them out much more efficiently. And the trick is, one of the things you need to be aware of is when you're getting time series data, and actually the energy data that was used in both of the research projects that we talked about before used energy time series data. And the timestamp that you get is the time of the last value in that series. So when you look at the data, basically to calculate the first time, you have to calculate backward from that last sequence of data. And the other thing that we support is also statistics. So in this case, we have an average. The data that we're collecting is over a certain period of time, and the duration that we give is the amount of time that average was taken, and the timestamp again is at the end of that sample. With conditions, again, we have normal, warning, and fault. The component is within, so normal means that we're within normal operating parameters. Warning means that we are going to probably fail fairly soon, and fault means that we have actually failed and something needs to be done. One interesting characteristic of conditions is that conditions can have multiple values at the same time. So we can actually have multiple faults. And this was done so we could represent things like syntax errors in part programs and other types of situations where for a single type of condition, we can actually have, we can represent multiple instances of a failure or something that happened, or warnings or so forth. The problem, again, events and samples, you can't have two values at the same timestamp. In conditions, you can have multiple values at the same timestamp. Availability is very important to MTConnect. When we first started MTConnect, we wanted to make it possible to represent any information that you can collect from a machine. And the only thing we could really agree upon within MTConnect was that we were going to be able to say whether or not data is available. That was like the lowest bar we could set. So there's only one data item that is required by MTConnect, and that is availability. And there's only two possible states of availability: when data is available, when data is unavailable. And any data item in MTConnect, when it occurs in the streams document, can also have a value of unavailable. That means that the data is unknown. So in this case, though a load is a floating point value, it can also have the value of unavailable that indicates that we don't know what the load is. Conditions also represent unavailability as such. The third document that we have in MTConnect is called assets. And assets represent the information model about a particular area. So we have right now cutting tools as being the one that we've published in MTConnect. And we also are now working on parts and inspection. We're also working on transformations and controller values. So basically data that you get out of the controller that are pretty much registers out of the controller and offsets and things along that one. So these are transactional, meaning that they don't change as often, but when they do change, they change as a whole. So a cutting tool can't change as a cutting tool is used. Various statuses and wear and so forth are all updated as a single unit. Assets are stored as a key value pair. So basically, if you think about some of the new NoQL databases like Mongo, Cassandra, HFS, S3, AWS, these are all what are called key value stores. So basically, you have a unique identifier associated with that information model, and that key then translates into that can be then requested. And that'll give you the entire document that's associated with it. And the document will then be interpreted by the application within that context. We do have the ability to notify whenever anything changes within that document. So instead of having to poll to see if things have changed within MTConnect, you can actually just subscribe to notifications on additions, updates, and deletes, and MTConnect will tell you when that occurs. For things like the cutting tool model, which is one that's currently was added in version 1.2, we have what's called the cutting tool lifecycle. And the lifecycle tells you about how this tool is being used in the use phase of that assembly. So basically, tools are made up of multiple parts. There's cutter body, the tool holder, as well as the cutting items, which are the inserts and so forth. And MTConnect has a way to be able to describe that tool and various critical measurements of that tool, like the length, the functional length, the diameter, and so forth of that cutting tool. As well, we also know about things like the cutter status, so whether it's new or used, and how much life is associated with that. So in other words, tools eventually wear out, and you need to be replaced. And then MTConnect, we can actually represent within this model exactly how much life is left on that tool. And if you look at a physical tool, this is actually how everything maps in. So these are pictures of real cutting tools. And all of these dimensions and all of these measurements that you see here are actually tied to another standard, which is called ISO 13399, which is the solid geometries, or the geometries of this cutting tool. So we use some of the same nomenclature. The codes that you see there, DC1, DC2, UF1, UF2, are all represented within MTConnect. So we have two models. This is actually going across all of our asset models. We have what are called the archetype and the instance. The archetype is the general structure of this tool that applies to all of the instances. So if you think about it as sort of a template, the archetype gives the nominal and the minimum and max values, but it's not an actual measured thing. When you get to the instance, we then start talking about an actual version of this tool, a build of this tool, and the measured values. We'll talk about that also within respect to parts. So you have a part instance, which is kind of your plan of how the part is going to be made. In the part instance, the actual data collected from the process and how that part, an individual part, was made, and all the data that was collected along the way of making that part. So when we look at the solid model and look at an actual tool and its measurement, we then translate that back into our model. So if you look at all these different names, like the various different lengths and diameters and so forth, Those are then translated back into MTConnect as a set of measurements, so you can see where the codes are then applied, as well as the actual values that come off of the presetter or whatever measurement device that you're using to be able to set your machine up with the actual lengths of these tools. The archetype itself is, again, sort of a simplistic version, and it contains things like the nominal, minimum, maximum. So the idea is with the cutting tool that you can validate that the values are within an operable range, but we don't actually have the actual values. As we go to the instance, we'll actually fill in those values. And here's the events that occur when an asset changes. So basically, these are the asset change events. Whenever an asset is either added or updated, you'll get this changed event, and the changed event will tell you the type of asset that was just updated, as well as that unique identifier, so then you can go and grab it. And that'll be covered more within the protocol section. In 1.4, we're going to be releasing the parts model for MTConnect, and that's going to contain traceability and things like work orders, production plans, the steps that are going to be used to execute the process, as well as what we're calling now activities, which are the operations within the process. And those are going to contain constraints on like tooling, process parameters, feeds and speeds, and all that kind of fun stuff. We're then going to contain within the instance document process data, so logging constraints that were violated and how that data is going to be collected. As well, we're going to be able to collect things in the future like in-process inspection, so inspection data coming off of the actual manufacturing process. And we're always going to be adding new asset types. And the thing is that you can actually add your own asset types if you want to. MTConnect provides just a general mechanism for storing any type of data as long as it's an XML inside of this model. So if you need to store something else, like let's say fixturing and work holding, you have some basic concepts around that, you can actually extend the model in MTConnect to support new asset types, as well as data items can also be extended. The last document model is what are called errors. And errors are just a simple document that tells you if you make a protocol level error, like you're not authorized or there's no device of that name, and so forth. We have a standard set of error codes and text that are come back from the MTConnect agent. Those have all been documented. As I was mentioning, you can actually extend out the schema as well, add new component types if you have new components that are relevant to your type of device, or new data item types or new assets. You can easily add them to the model. And I think we'll be stopping here. So I think we'll stop with protocol. We've gone for about an hour, and I'll just cover this. I think we'll cover that in maybe another section.
Okay, so this is a good place for us to stop right now. And but before we go, Will, can you share with us a little bit of the free tools and tech, as well as some of the resources that are available?
Sure, yeah. So one great thing about MTConnect is that we have a lot of open source technology that's already available for you if you want to get started with it. We have this GitHub site, for everybody's familiar with GitHub, GitHub/MTConnect. If you go to that on the web, you'll find there's a reference version of the MTConnect agent, which is in C++, and you can just download it. There's a pre-built binary for Windows, and there's instructions on how to build it on Linux. As well, there are labs in C# that use an open source .SDK, which allows you to easily build adapters, as well as we have an application lab, which shows you how to build applications. And we have a lot of other bits and pieces. Joel Neidig has graciously donated things like a Google Glass demo, which is really cool, a Unity 3D demo for the Xbox, and various other technologies are up there. So it'd be great to just look around, and you can see some examples of how MTConnect has been used for doing some fairly interesting things, as well as the machine-to-machine integration project that I talked about in the beginning is actually up there, and it uses the ROS industrial simulator to provide a fully functional implementation of a robot simulator with a machine tool simulator, so that's pretty cool as well. We also have libraries. If you want to do stream parsing, and we'll talk about that in the protocol section. Later, we have the stream parsing libraries that have been written in multiple different languages, C#, C++, and et cetera. And you can then get real-time data from MTConnect and use it within your application as well. We also have some additional resources available for you for things like R. And R is a great language for doing machine learning and statistical analysis, and it's available up there, and there's a Vimeo link as well. We've actually created some MTConnect scripts that are available from System Insights that you can download, and they're open source, and that allow you to play around with some MTConnect data. There's also some really interesting new resources that are available, like Azure Cloud and Amazon have these platforms, IoT platforms, that are getting more and more robust and more interesting every day, that allow you to do things like stream processing and event management and storage and complex event processing, all kinds of fun stuff. And most of these things you can get for free, so there's a free level of usage, and there's going to be a lot more resources on that available in the near future. So to get started, you can use the open source tools, as well as we have an agent that's available for use that's running 7x24, agent.mtconnect.org, and that will just stream data to you, and you can start playing around with the data. And we have additional data sets that are going to be made available as well to play around with. So if you want to just get an idea of how to deal with data from MTConnect, turn it into like comma-separated formats, CSV formats, and then import it into R and play around with R. There are tools out there that will get you moving and get you a lot of really, really great, be a really good head start.
Terrific. So, okay, I know that you've got somewhere that you need to go, Will, so I'm going to say thank you very much for you. In fact, if you want to cut out right now, I'll tell Helena to turn herself back on there. Hey, there we go. And we'll see you, and we'll set up the next one and see you at that one where we'll finish it up, do the final thing. But so, Will, you go ahead and take off. Helena, so let's. Thank you, Will. Thank you. Helena, let me just pull this screen up over here. And I know that we don't have the update of the short URL put in there, but this is where they can contact you for more information, as well as where the Facebook page on the replay and the archive. I'll have that corrected with the short URL. But with that, is there anything else that you'd like to share with the students who are watching?
That's it. Just feel free to email me or call me if you have any questions, concerns. If you need help in any way, shape, or form, I'm available.
Okay, sounds good. You know, this is a terrific product and a terrific student challenge that I think you guys are. Okay. Wait. I got one more thing that I need to ask you, Helena, and that is, this is very important. You know, you got to acknowledge the sponsors, right? Where is the financing coming? Where is all this money coming from for the student challenge?
The money is coming from the Office of Secretary of Defense, Defense-Wide Manufacturing, Science and Technology Programs. And in fact, the project is being executed by AMT, the Association for Manufacturing Technology, MTConnect Institute, NCDMM, which stands for National Center for Defense Manufacturing and Machining, and U.S. Army Binet Lab. And we're doing it in partnership with SME, Society of Manufacturing Engineering, and NTMA, National Tooling and Machining Association.
Okay, yeah, that's important to make sure we acknowledge, the sponsors, so to speak,
Yeah.
and who's doing all the work here, right? It's not just Will.
That's right.
It's not just Will and Helena.
That's absolutely correct.
And Steve. not just us, all right? So, so we'll be back again for a fourth, and I'm thinking final. There might be more webinars, but for this particular series of explaining the whole thing, we'll be back for a final one very soon, and we will make sure that we put that out on the internet for everybody as well. So thank you, Helena, Orange Small Room.
Well, thank you, Steve.
And I will see you in the next. See you on the next webinar.
Yes, see you. Take care.
Okay. Bye.